So, I'm gonna welcome Travis to the stage. Yes. So maybe you can introduce yourself.
Sure. Hi, I'm Travis. I'm the site manager for Sweden in evolution engineering. We have this office here in Stockholm, and we have another office in Gothenburg. So we do cross-functional things here as well as make a lot of games. I'd like to thank Lashazar for actually initiating this whole thing. So we're very happy to host this and very happy to see you guys here. We do a lot of work here, and he'll tell you a little bit about our systems. Right now we're about 20,000, a little bit more than 20,000, 20,646 employees now. Oh, yeah, okay. Clicker. Yeah, right, and we're worldwide, we're global, we're basically everywhere. We've got about 35 building projects going on at right now in the world, mostly in North America and Central America. We've got, you can see here. Hired about 1,000 people per month last year, mostly presenters on the live side. We're targeting to get up to about 30 to 35,000 in the next couple of years. We have 40 studio hubs right now, 15 broadcast studios, Evolution and Izugi, who's also a live studio. And we've got 8 engineering hubs, and this is one of them. Right now we got about 1,000 engineers. We're planning on growing about 10% this year. So Evolution Group has 7 brands. So Evolution, Izugi, NetEnt, which is here in Stockholm, Red Tiger, Big Time Gaming, No Limit, which is also here in Stockholm. They sit over here, and DigiWheel. We also had another acquisition here recently of a smaller company. Swedish company, founded in 2006, operates fully B2B, delivers turnkey solutions for operators in one single integration we call the one-stop shop. Listed on NASDAQ since 2015, and we're really set on growing. So, Oh yeah, there was a bunch of little things. Animations. Oh, I don't usually do animations in my slides. So. Okay. It's okay. Anyway, thanks a lot for coming. I hope you have a great evening, and let's look forward to doing this in the future as well. So thank you, guys. So there you go, sir.
And my name is Lachazar, and I'm going to present you a bit about the technical part of evolution. We are using Scala 2 and 3 with type level, stack, and akka across the entire company. We are very, very happy with it, and we use a lot of type level projects. We also use event sourcing with akka persistence and Kafka Journal. We have our own Kafka Journal plugin that is partially open sourced, and actually the team that develops or works heavily with akka persistence is also in Stockholm. So this is where platform developers job offer comes in. We also do development with slot games, and we also have openings for slot games developers. We have our platform handles more than 100 million transactions a day with a sub-second latency. I'm sure that this is true. And we have multiple open source projects hosted at github.com, Evolution Gaming, and this is absolutely true because I've seen it. We are hiring in Stockholm and in Gothenburg, game developers with Scala, platform developers, and I will welcome you to check our job offers using these QR codes that are available to be seen later as well. And I really, really thank all of you for coming. I'm really happy that we revived this event. It's really heartwarming for me to see everyone. And with this, I want to invite Oleg, who is evolutionary from the Amsterdam office, and is going to talk about capture checking with Scala. So welcome, Oleg.
Hello, everyone. I'm Oleg. I'm a Scala developer, also just a lover of functional programming and type systems. And let's start from a small physical exercise. So raise a hand if you are a Scala programmer or just do Scala programming from time to time. So unexpectedly, a lot of you are on a Scala meetup today. So, okay, raise a hand if you are using IO monad or Zio or something like it. So at least half of you. That's quite a lot. So people from the last part. How many of you like it? Almost everyone. Oh, it's surprising. There was an interesting, mostly epic thread on Reddit 6 years ago, and some guy just asked, what are benefits of IO monad? Because, you know, our company moving towards it. And the person who answered them, among others, was no other than Martin Odersky, creator of Scala. It's a very good question, and maybe you shouldn't use IO monad. Maybe you just can use some magical ticket called can.io, some capability that allows you to use some dirtiness in your function, and if function doesn't use it, it's pure. Some other person mentioned that it doesn't make sense, because if you have this magic ticket once, you just put it in your pocket, and every time when you just want to do some allegedly pure things, you can just use this ticket secretly, and nothing would work. And Martin Odersky answered, that's an excellent observation. We need to change type system, maybe, for this idea to work. So, some time passed along, and Martin starts to talk a lot about some mystical Caprese project and a lot about direct style programming, meaning style programming without monads and for comprehension and all this stuff. And he starts to talk about capture checking, and actually capture checking now in the Scala compiler, in some recent versions of Scala 3 compiler, and this is part of the official documentation for some time already. And actually, in the recent Scala 3 roadmap for 2024, maybe the only one thing that they would like to do, the Scala Center, for improving the language and the library, they want to implement capture checking in the student library. So now a really scareful question. Raise a hand if you know something about capture checking and how to use it. Oh, like 3%. Okay. Hmm? Yeah, but the main idea that actually something happened in Scala 3, right? And basically no one knows what. So hopefully today we'll talk about Scala 3. So we will talk about some and how is this capture checking actually related to effects? How it actually implements the idea of effects in Scala language or I/O or something that could just move I/O out from your language. So first we start with some imaginary Scala that would have effects. Then we continue with like half imaginary Scala that almost like that we have. And then we finish with some examples from real Scala and how the compiler works. So how many of you know something about effects, system, algebraic effects, something like that? So, for rest of you, there is a thing that called effects. That basically everything that can happen during the execution of various code, everything that could come to mind, that thing that could happen, mutation of some mutable state, and everything could be considered as effect. But actually, only some people would say that is like normal effect of the code execution, and this is side effect. And you know, this is really a really subjective thing. So we have some scale, and different people have different tolerance to effects. So some people would say this is non-effect, this is not normal behavior of function, and these are real effects. But some people with higher tolerance will say otherwise. So let's imagine some Scala that have effects, right? So this is like normal Scala. How many of you could read the code currently on the screen? So yes, a lot of you. It's normal Scala. It just works with normal data types, options, vectors, etc. So let's add to it something new, some special syntax that you can write after the method, which recognize that this actual thing could do something during the execution. So this specific, like the simplest effect, abort. Somewhere during execution of this method, it could just stop executing. It's like the simplest effect. And these effects, they are like parasites. They are spreading. So any other block of code that actually use something that is effectful becomes effectful, though these methods will also have abort effect because it uses this function directly. But you can actually somewhere handle this effect. So now you can just put some block of code that use this read-ins, and then you put it into a handler which like receive this block of code and safely handles this effect. So that's how effect should work in our imaginary language. Also, if you don't like methods, you can use functions. So in this imaginary Scala, but not only in imaginary one, we will use these thin arrows to talk about pure functions. So fat arrow is like a probably impure function that can actually do anything. And this thin arrow is pure function or function with declared effects. It cannot do anything. It can only do, from the dirty things, can only do things that are enumerated here in the effects section. So you can just rewrite this whole thing via function types that declare their effects. So to introduce an effect in your language, you should use some form of top-level construction, something that looks like trait definition with some abstract methods without a body. Next, you can just use these methods as they were defined in this object. So, but actually, each of this method is not defined yet. It somehow delegates real things to the handler. And this handler, I specifically used this try-catch expression because these handlers in the all languages that we could talk about instead of this imaginary Scala, like Coca, Frank, or Unison, maybe you heard about it. These expressions really looks like, this exception catching. So you just have some expression, as you call this. This is something like called by name. Do you recognize this syntax? Like you have the arrow before some expression and some effects that could happen during this execution. So next you execute this code, and then you catch the first invocation of your effect method and tell what to do with it. So, but maybe you don't have an effective invocation in your block. So then you can just call catch up your result and return it. Among other things, effects can actually combine. So you can have two methods. They can have different lists of effects. And if you use them together in a single block, they can actually, generate a new list of effects that is a union of all effects in these methods. So they can compose. And also, if you just use some different methods that are referred to the same effect, you don't need to repeat yourself. So each effect should be mentioned here only once. So somehow all invocations of this single effect, they should be collapsed to each other, like monad would collapse several layers to a single invocation, but independently of each other. So these actual effect signatures should be inferred. So in our imaginary best language, these effect types should be inferred automatically by compiler, but only if we're lucky. So let's talk about one of the main features of this effect system. So consider we have this simple definition, like we have this square root that stops execution if it receives negative number, and we have this function square sum, squared sum, like sum of the square roots. So do everybody understand what's currently on the board? Okay. But what if we actually want to optimize this function a bit? So it's a carried function. It receives one argument and other argument, so we can actually pre-calculate square root of the first argument before we receive second argument. So now let's try to guess what possible signatures should our compiler infer for effects. So this signature said that we receive float and another float, and then using the effector board, we generate a resulting float. Is this signature actually plausible? Does this actually solve this, our effect thing? How do you think? If you think this is nice signature and you will like it in the effect language, put your this finger up. And if you think that is like something bad, you put your finger down. So let's start voting. So a lot of you don't like this signature. Why? Obviously why? Because here we have some effect, right? And it doesn't recognize, because if we put only one number, we already have the effect. And it doesn't reflect it in the signature. So it was a wrong signature. So what about that? We have an effect, and after we have permission to abort, we can just reuse it in this function, if this signature correct. So vote. Most of you vote negative, and this is correct. Maybe this signature that actually asks to abort twice after the first argument and after the second argument, maybe this will work. So vote, yes or no. Most of you, some of you just doesn't like anything, but actually that is actually a good signature for this function. So let's see for a minute what we just discovered. So these actual effects, they kind of like, some instances of some undefined traits defined at the top level. But what you can actually do, you cannot just push them to the inner lambda bodies. So lambdas cannot actually capture these permissions to do these effects, right? This is more complicated, and maybe just even without diving deep in this code, you can guess if the first signature correct, yes or no. Okay, it's too hard. Let's not spend the time. We have an effect here before we receive second argument, and an effect here after receiving the first argument. So this signature could not be accepted by our imaginary compiler, and this signature should not be accepted by our imaginary compiler, but this should be. We should actually mention effects exactly in the place where they happen. So this theoretically allows us to replace a lot of, our structures, our known monads, with some form of effects. But what could actually, these things are composed much better than these monads. You can actually, you don't need to, push one into another, invent some monad transformers or whatever. They just compose automatically. So let's try to understand one of the main things about effects and why we cannot have nice things in our language. How should they work actually during the effect handling? So we define this very simple effect that have method next without parameters, and it only just only generates some integer number. And we just try to write different handlers for it. So this is very simple handlers. It takes a block that have generate int and some other effects. Then it tries to start this block, and if it encounters the method invocation, it actually says, okay, I have a value to generate, so I can do something. So he can provide, actually during this effect execution, he can provide. And to provide, most of these effect languages, they provide you with this magical function that usually called continuation. So this resume function, if in this block to the right of the case match, you have this magical function that allows you to resume your execution after you encounter first effects, and it should have this exact signature. It should have should receive the promised returning type of your method, and during the execution of the whole of the rest of your block, you can encounter these effects and maybe these effects as well, because it can encounter more than once in the block. So you should have this magical resume function, and just to resume, you can just call it. So, but it's not. It's magical in the sense that you will automatically have it, but it's not magical in the sense that it's some magical syntaxes. No, it's just a normal function of this type. So we can use it as a normal function. You can actually handle your internal resuming thing after you resumed with some other handler. So for instance, this handler will just increment the number each time. So hopefully it will just generate ints one after another. This form will work as an exception. So first time he caught some effect, it just cancels all the execution, so it does not use any resuming at all. And it just, returns some default value. You can also delegate to some other effects, and you can actually add the code before and after resuming. So this whole thing could just turn to some resource management or dependency injection. And the most mind-blowing examples, don't dive deep into this code, but we actually can implement something like backtracking search with this thing. We can actually call this resume function multiple types, and each time this resume function should resume from the same place. So we caught the effect, and your runtime somehow need to provide you some continuation that will continue execution from this exact point each time when you call this function. This is like pure magic. And this pure magic should be implemented automatically by your runtime for effects. And this is actually really hard. So comparing effects and monad, effects are automatically composable. They require very special runtime. They can partially handle, like they can pick some effect, handle it, leaving other effects in scope. And it actually cover a lot of language features. Like in other example, we covered backtracking and resource management and, just generating something and just a lot of language features with just one. And actually you don't know before ahead what will happen. What would happen when you use some effect. You only define the actual behavior when you define a handler. A lot of libraries in different languages try to, reach this gap before effects and monads, but unfortunately, even the smartest ones, like Kio, the most recent library, they cannot actually do it because you need very special runtime for it. And the only runtime we have is JVM. So let's talk about a little bit more realistic things. So, state monad, right? How many of you use state monad from time to time, maybe in unit test or something like that? So, like, few people. Okay, how many of you know what state monad is? So, some people know. So, this is just a pure functional way to abstract over something that looks like mutable state. But it's not mutable, actually. You just take the old state and return new state as a new object and some value on the road. And you can provide some monad-like signature for it, so you can use it in for comprehension. And you can define these methods that would just give your code look and feel of mutable code with a single mutable, global variable. Then you can write some unreadable code using it. What you actually should concentrate on this giant code, these lines. If you didn't understand yet what I mean, these lines. Because you have only one mutable variable, pseudo-variable in this state, you need to actually combine all of your state inside this one giant object and copy it, create a new copy, allocate, and allocate time after time, every time when you just change something. But we are smart programmers. We can do better than that. We can do this better, just object mutable, right? So problem solved. Obviously, you cannot solve problems by the direct mutability without any controlling, or else all this functional style loves thing would not exist. So yeah, so this actual mutable thing give us a lot of danger. So we wrote something that looks very enterprisey. We can just report some state with some name, producing some strings, but we executing it, it seems it doesn't work. Why it doesn't work? Because this function report state doesn't actually report the state that was at the time it was called, because it refers to the state after it receives a name. So this is the main culprit, right? So we have this my state somehow captured in this lambda. And the main trouble of this mutable thing that we at the same time have two places, two different objects, or two different pieces of code that refer the same mutable object. So because of that, they can just not copyrate. And this not copyrating between different parts of code that use the same mutable object could lead to unexpected results. Right? So what we can do, we can just fix it, just uncapture it, take it out from the lambda, and our code becomes correct. But we need to think how to prevent this in the future. So, but what if we write this beautiful, probably functional code, and we actually know that this data that we constantly copying, and reallocating is actually the only one reference, the only one existing in the whole program reference to this data. Actually, what we can do, we can replace any copying with the mutation. And it would be safe because no one can see. No one can see. We forgot about this object. We just construct a new object and throw this on. So after this method, there will be no reference to the old object. It cannot be used. So this translation is safe. It actually brings us to two ideas that I used in the computer science. So one thing is in the runtime. We can automatically rewrite some things into from this copying to mutation. It just uses in some languages. But what we actually do instead, we can require for some objects to have the only one unique reference at this point. It's called uniqueness types. It's implemented, for instance, in the language clean, which is used in the faraway land called Netherlands. So in this unique mutable state actually allows us to replace this form of functions with this form of functions. You hear this symbol, how is it called again? Caret, okay. You see this caret, and this signifies this is unique reference to this state. And this is semantically equivalent to this. This is the same thing. Because we actually mutate and show, yes, we know this reference unique. So just pretend that you have some state and you just lost it and you just have the new state instead of it. So we make mutation safe. We make it semantically equivalent to some pure functional code. This is what uniqueness types about. So uniqueness types actually forbid you to write such code because you receive some reference, but you are unresponsible. You try to capture it inside the lambda, and you shouldn't do it. And you should automatically, with help of compiler, write it to the proper definition. So what actually this allows us to do is to think of these unique references to the mutable objects, not only just safe way to do without allocation, but we can think about unique file. What is this unique file? It's some mutable unique reference to something that mutates outside our random access memory, right? It just mutates, but on the disk. Or I/O. It could be unique object that refers to the whole real world that we can mutate in our program. And each time we use it, we only have unique reference to it, and we not allow to capture it, to clone it, to copy it. We can just use and let it go. So actually, we can start thinking about uniqueness as an effect. And as we've seen before, functions like this that have this unique reference to some objects, we will have to rewrite, if we try to refactor them to some form, like this form, we have to actually refer to this unique object every time when we use it. So in every stage, when we actually try to touch this unique reference, we need to refer this. So this type system works actually as type system with effects, but it has some differences. So in unique types, we can use usual types. We don't have this magical resuming function, so we cannot implement this language features using this magical resume function. We can refer to this by actual names, so we can have two unique files and program at the same time. We don't have to just, this single file effect. And we can actually, if we don't like to refer to things by name, we can use implicits or givens using this syntax and use types. We can have several vars of the same unique types. We unfortunately don't have some inference. So these unique references do not, inferenced automatically like effect. But we can do something form of composition of them. So what form of composition are we talking about? So imagine we have some reader and it captures this unique reference, and it itself should be unique. But to create this reader, you need to do some, computation. So actually, how do we guess? So if we construct unique values from unique values, how can we guess which actual variable is promoted, which variables are captured in this unique, which reference is released and which is transformed to a new unique reference? This is a good question. And Rust has its own, approach to this. It has something that's called lifetime. So you can just mark different unique reference by special things that called lifetimes of this reference, lifetime of this reference. And because the result type references only this lifetime, we know that it encaptures only this variable. But we can do better. Instead of all this type crap, we can just refer directly by name. And as you may have guessed, the whole thing we talked about is actually implemented currently in the Scala compiler. So these unique types are actually prototype for the thing we are called capture checking in Scala. So does Scala 3 actually have effects? We don't have a lot of time to talk about it, but we can just short walk around the formal rules. So every type in every place can have a capture set. Capture set is this thing over here. So every capture set can refer all the names that it knows something about. And these capture sets can only refer to some variables that have this, captured tracking. So this type is tracked, so it can be referred, and this is untracked, so it cannot be referred. These capture sets, almost like effect, things, they can consist of several types. And the best set is empty set. That means our thing does not capture anything. The worst set is called cap. It's like analog of any. And this is the only capture set that can capture something that is not named, that some variable that you lost sight of. That's like super, super duper dirtiness. And they have this, subtyping relations because we are in Scala and we like subtyping between them. So next, just a quick run over everything. We can start just replacing all the things with these captured, with these tracked elements. So we can just imagine that these strange objects is probably mutable or some other references at which types are maybe marked with this capability annotation. They are kind of like effects, and we can just use this our implicit things like using and giving to talk about that. So we can replace reader by the normal value. We can just replace some mutable states and have many different mutable states at the same time. You can write it one style, or you can just translate everything into methods of these mutable objects, because those are not effects anymore, that are normal references. They can have methods. You can actually use some form of, built-in capabilities. So this can throw capability is controlling some exceptions. It allows you to throw something in some block, and it could be also used as built-in capability. And when you write some code using this imaginary effect-like unique variables, you don't need for comprehensions or do comprehensions. You just can write it in direct style. So I need to get to the end, right? Okay. If we have a few more minutes. So this is how it should or can like. So it actually reminiscents a little bit of this tagless final thing, but it works without for comprehensions, and it works in direct style. But it doesn't provide anything that monads provide. It doesn't provide you concurrency things or this multiplicity things or something like that. So, and we actually can take some data structures like lazy list and replace some actual data structures with these capabilities, capability-like effects. So we can just say that any block that receives this consumer is actually a lazy stream of values. And we can produce this lazy stream of values, just feeding some consumer, some elements. We can take some block that have this receiver and provide actual value of this consumer, of this capability type to actually handle this effect. This is handle-like situation. Handle-like situation, just creating a value of your type. So you can just eliminate this stream effect, generate an instance like that or like that. And these blocks of elements with effects can actually work like some form of lazy data structure. We can write map for it, flat map, filter, all the things that operates with these blocks that implicitly requires our capabilities. And actually, to compose those values of the lazy list, we can use this little bit scary, a little bit cringe, direct imperative style. So we just, call three methods one after another, and this is something form of concatenation. Just emit something into your object, and you just generate new elements of your collection. So this is basically it. This is how we use them. We use these capabilities with the new typing thing, but the actual thing we are using implicits, but a little bit more lawful implicits that allow us to use mutable objects inside implicits. And this is actually what is all about, this direct style or whatever. So we use all the machinery of our implicits. We use context function. We don't have inference. In implicits, you always declare these implicit blocks manually. You can just define these values because implicit values is just normal values. You can use these contextual lambda blocks, like in here. These methods, as you can see, you don't need to pass this mystical argument into these methods. You can just write these implicit blocks. That's how contextual blocks work in Scala 3. And you can actually embrace old school imperative programming, but imagining that you're doing some new functional programming style. But actually, it's not an imperative programming anymore, because I mention these effects in this local scope. Nowadays, it just becomes a fancy syntax for effectful language, and this is how we use it. So that was it. Thank you very much for listening. And these are, again, our positions. Any questions? No?
Let's take questions if you have any. Yes, I'll give you back the microphone, Oleg. And you can just shout out apparently there are microphones everywhere here, I'm told. So. No, they're in the roof actually, and hopefully they capture what you say on the video as well. So,
okay, thank you. I have two questions. The first one is, I guess, this transition to this style of programming would require significant changes to integrating with the standard GTK library, right?
No. You don't need anything from JVM to do that. But of course, you don't have concurrency as a monad anymore. So you have to use Loom for concurrency, and you will have all the all the fall pits of this approach and everything. So you can just look into Ox library or Gears libraries that use it and think how they can actually have this capture checking in the future. So next.
Thank you. And the second question is: are these foundations enough to implement something like a borrow checker in Rust, or not?
Borrow checker? No. Unfortunately, this is a very weak form of substructural typing. So what you are referred to as some substructural type systems, and different substructural type systems could express each other, and using like the linear logic, one of the most restricted ones, you can re-implement a lot of other substructural, but this is one of the weakest one. You can basically not express linear or a fine logic using it, only some form of unique types and maybe something like that. That's it.
Yeah, thank you. Okay, so I guess it's, I understand, like it's impossible to implement the tracking of the memory allocation in the user event code. But let's pretend that a compiler has the ability to synthetically generate sort of like values.
You can actually write safe interfaces. So what you're maybe asking about, if we can write the same level interfaces of same level safety for memory or something like that, and maybe we can because we can capture check not only implicit parameters, we can capture check local variables, all of that thing. We can define structures that different parts of them can track capture of each other. But I haven't included everything, but because all of this is just speculation. It's just a question of future work on this subject. Thank you, everyone.
Yes. Yes, Oleg, all the way from Amsterdam. Let's give him a hand. Okay, so we'll have a break so you guys can eat some more and have some more drinks.